nature has had 3.8 billion years to test and refine its designs. The spiderweb is not just delicate, it's incredibly strong, light, and efficient. Every thread is placed with purpose. Like the spiderweb, the ant's underground home is a masterpiece of engineering. It regulates temperature, manages airflow, and organizes space with no wasted effort. These natural structures reveal how form, function, and performance are inseparable in nature. Just as spiders and ants build with precision and purpose, biomimicry invites us to learn from that same natural intelligence, translating life's tested strategies into human-designed solutions. It is a design approach that looks to nature not just for inspiration, but for instruction. It's about studying how organisms solve problems, how they regulate temperature, gather energy, manage resources, and then apply those same strategies to human systems. Biomimicry is not about copying the appearance of nature. It's about learning from its logic. Plants grow towards light, conserve energy in drought, and heal themselves after injury. Efficiency in nature is dynamic. It adapts, it regenerates. It's the responsive intelligence that we seek to bring into architecture and design. This logic of adaptive efficiency becomes especially relevant in desert regions, where architecture must respond to extreme environmental challenges with the same resilience and precision seen in nature. Across the vast stretch from Saharan Africa to West Asia, residential architecture must do more than provide shelter. These regions face relentless solar radiation, scarce water, sand-laden winds, and most critically, extreme temperature swings between day and night. In desert climates, daytime temperatures can soar above 45 degrees Celsius, only to plummet at night, dropping over 20 degrees Celsius in hours. This rapid fluctuation places intense stress on building materials, energy systems, and human comfort. So how do we design homes that can adapt to these extremes, staying cool in the heat and warm in the cold, without depending on external energy? The key lies in passive cooling, a principle deeply embedded in nature's own designs. Nature becomes our guide, offering time-tested strategies shaped by survival. Through biomimicry, we can translate these systems into architecture that is not only energy efficient, but also resilient, sustainable, and deeply in tune with its environment.
To understand how biomimicry plays out in the real world, we're comparing two buildings in hot, arid regions, one ancient, one modern, the Agazadeh House in Iran and the Eastgate Center in Zimbabwe. In this case study, we're examining not only the performance of each building, but the materials, labor processes, and environmental strategies that shape them. If we're conducting this study on the ground, we'd want to interview laborers, track energy performance, and understand the life cycle of materials used. For now, this comparison gives us insight into how ecological knowledge is embedded into both tradition and innovation and why it matters today. The Agazadeh House in Abarku, Iran, is a striking example of ancient passive cooling design, rooted in both local knowledge and natural principles. Its most iconic feature, the badger, or wind catcher, channels air into the building and cools it through natural ventilation, without relying on electricity. Built entirely from sun-dried mud bricks and clay plaster, the structure reflects deep ecological sensitivity, using only what was locally available. This not only minimized transportation costs and environmental impact, but also empowered local labor traditions passed down over generations. Agazadeh House is more than just a beautiful relic. It's a reminder that sustainability isn't new. Its design is inherently resilient. It performs passively, even in extreme desert heat, and requires minimal maintenance. These are qualities we seek in modern architecture, yet they existed centuries ago through an intuitive understanding of nature. Now, fast forward to modern-day Zimbabwe. In Harare's dry summers and cool nights, the Eastgate Center responds like a living system. It is one of the most well-known examples of biomimicry applied to architecture. Inspired by self-regulating mounds of African termites, architect Mick Pierce designed a building that mimics the termite's strategy: regulate internal temperatures through strategic air movement, insulation, and thermal mass. The building breathes, drawing cool air at night, releasing heat during the day, and maintaining a stable indoor climate without conventional air conditioning. Like the Agazadeh House, Eastgate uses local materials like concrete and brick and was built using local labor, reinforcing the idea that sustainability doesn't have to mean high-tech or imported systems. The Agazadeh House and the Eastgate Center both tackle extreme heat, rapid temperature swings, and limited energy using passive cooling, local materials, and biomimicry. One reflects ancient, low-tech wisdom, the other modern innovation. Yet both show how learning from nature, whether through traditional or engineering, can lead to sustainable, climate-responsive architecture.
This comparison not only highlights different tracks to climate-responsive design, but also sets the stage for a deeper discussion about how biomimicry, when combined with local materials and labor, can push sustainability beyond comfort to achieve affordability, equity, and cultural continuity. In standard construction, buildings often rely on imported materials like concrete, steel, and synthetic insulation. These come with high costs, not just financially, but environmentally, and they often perform poorly in desert extremes. Now contrast that with locally sourced materials like adobe, rammed earth, clay, palm thatch, or compressed earth blocks. These materials are abundant, low cost, and naturally suited to the climate conditions of arid regions. They also carry biomimetic value. This principle appears in clay tiles and bricks across sub-Saharan and West Asian construction. When combined with passive cooling, it greatly improves comfort without external energy. So what does this all mean? The Global South doesn't need imported solutions. It deserves innovation rooted in its own wisdom, local knowledge, local labor, and local materials. These are not signs of limitation, they are tools of resilience. In hot arid regions, passive cooling becomes a key strategy, reducing dependence on expensive, energy-intensive systems by using design to work with the climate, not against it. Today, as the impacts of climate change grow more severe and energy inequalities rises, studying and applying these strategies is more urgent than ever. For the Global South, this is not about sustainability. It's about survival, self-resilience, and long-term justice. Biomimicry teaches that survival is not about dominance, it's about harmony. This is how we build better futures from the ground up.